Hello students, good day, and in this video we will learn about the functions. Before this we have started the topic with the name discrete structures and discrete objects that we usually encounter in computer science. Uh, so in the last lectures we covered about the set theory, and we saw that what are the set notations and how the sets are used and how the sets are represented, and then we saw what are the set operations that we perform on that, and we widely use this set theory in computer science. So in the upcoming courses in the later semesters, you will basically apply all these theories that we are discussing um, in this course in different other courses. So today's video lecture will cover the functions, the basics of functions, that what are the functions and then how we will use it in the computer science, right? So this is the section summary that we will be learning today. So we'll see what is the definition of a function. We'll see some terminologies like domain, codomain, image, pre-image, and then we'll see the different types of functions. Basically there are three types of functions. One is the injection function, surjection function, and bijection function. What are those? We'll be discussing in this video lecture. And then we'll talk about the inverse function, right? After that we will discuss function composition, how multiple functions, two or more functions, can be composed to form the new functions. Then we'll see how we can graph those functions. So since we have the functions, can we plot the graph out of those functions, and how we can do that? Then we will discuss about the three special functions in this video lecture: the floor, ceiling, and factorial. So these are the special functions. We mostly use these in the programming languages. And at the end of this lecture, we will discuss about the partial functions. We'll see the definition only, what are the partial functions. So let's start with the formal definition of the function. What is a function basically? So assume that we have two sets, non-empty sets, set A and set B. Let's take one example. Set A is a set of students. For example, this is set A, right? Set A is set of students having different members, elements like Ruby, Sandeep, Williams, Kathy. These are the set of students. And we have another set B, the set of grades, right? So for example, A grade, B grade, C grade, D grade, and F grade. So what does it says? It says let A and B be non-empty sets. So the first condition is the sets should be non-empty. Then a function, we denote it with a small f, from A to B, right? Function f from A to B, we denote it like f colon A arrow B, right? Or you can say f such that A employs B. What actually it means is an assignment of each element of set A to exactly one element of set B, right? So what does it mean? We are having two non-empty sets. What we want to do, we want to assign the elements of set A exactly to one of the elements of set B, right? So for example, here if you can see the students, Ruby, we have assigned one element of set B, that is A, to one element of this set A, that is Ruby. So we assigned A to Ruby. B, we assigned another element to a set of students, set of A, that is Sandeep. So for all the elements in set B, we assigned from set A, or we call it mapping. We map from the elements to elements, from the element of set A to this element of set B. So that's what it says. Just read it one more time. So we say that F A employs B is an assignment of each element of A to exactly one, right? Exactly one element of B. What does it mean? Ruby is one element, A, B, C, D, E, F, these are the elements of grades. So Ruby can have only one grade from set B. So it's not logically possible that one student can have two grades at a time. So I cannot say that Ruby has a grade as well as he or she has a B grade. That's not logically true, right? So that's what it means. Exactly one element of B, right? So again, B is an assignment of each element of A to exactly one element of B, right? And then we write it like this. We write F of A equal to B. What does it mean? We have mapped this A from set A with the help of function f, and the result is b. And from mathematics you usually you encounter like this: y is equal to f of x. That is again a function, isn't it? So what actually f is a function that for some value of x you map it to the y, right? So since this is the same concept, right, that you have studied in your mathematics classes as well. Okay, so why we write f of a is equal to b if b is the unique element of b assigned by the function f to the element a of a, set A. So that's what I said. I mean, one unique element is assigned to the set A, right? Here you can see in this animation the same thing. So what happens? F sends each A belongs to the set A. Each A belongs to the set A to only one of f of a, that is nothing but the b, right? F of a, element of b, right, that belongs to b. So f sends all of a to f of a, right? All of a, and this is called f of a since this is the mapping of all the functions, right? So that is basically the subset of the b, right? So what do we mean by that? We will be coming to this point once again after one more slide, right? So what is the function? Function is basically assignment of each element of A to exactly one element of B, right? Okay, so another way to define the function is a function f such that A implies B can also be defined as a subset of A cross B, or in short we call it a relation, right? We know that what is A cross B? This is a Cartesian product of two sets, and as a result we get the ordered pair. I mentioned you in the last lecture. So that ordered pair we call it a relation, right? So f such that A implies B can be defined as a subset of A cross B. This subset is restricted to be a relation when no two elements of the relation have the same first element. What does it mean? So for example, if we have set A and set B, and then we got a relation like A1, right? What does that mean? This A is member of set A and 1 is member of set B. That means A is mapped to 1, right? And then there is another ordered pair B comma 2. That what does this mean? This B is member of A and 2 is member of set B, and B is mapped to 2. So only then this is called a function if we do not get the first member the same member. That means if I have one more something like that, a comma 3, if I get this as a result of a cross b, then we have this. That means a is mapped to 1, a is mapped to 3 as well. That is not possible. I mentioned it in the previous slide. So you have exactly 1. So that means this is not a function at all. So this subset is restricted to be a relation with no two elements of the relation have the same first element. So the first element must not be similar when we produce A cross B. Then only we can say that this is a function. If we have multiple uh, uh, the first element same multiple f element first elements, this is not a function, right? So specifically a function f from A to B contains one and only one ordered pair A comma B for every element A that belongs to A. That's what I mentioned here in this example. So we can write it like for all x, x belongs to A implies there exists some y. For this x, there exists some y for the ordered pair, right? So for all x, for this x that belongs to A, we can map it such there exists some y, but for this y such that the condition is y belongs to B and x comma y belongs to function f. All right. So what does that mean? X can be mapped to y with this condition. Y belongs to the set B and x and y, this ordered pair belongs to f. Y belongs to f because this is the mapping of x to y, and that is only done with the help of f, right? And for all x comma y1 comma y2, what does that mean? We have the x from the set A, y1 and y2 from the set B. We can do the we have the definition for all x comma y1 comma y2 such that x comma y1, the first ordered pair, belongs to the function, is mapped with the function f. X is mapped to y1 with the function f, and x comma y2 also mapped with the function f, right? So belongs to f, right? This implies y1 is equal to y2. What does it mean? It means if we have something like this, we have multiple first numbers a and a, then what does it mean? It means 1 and 3 are equal, 1 equal to 3, if we are talking about a function. If it is a function, if a is mapped to 1 and a is also mapped to 3, that means they both are same. But I mean, it may be true or it may not be true in some cases. We'll see the example. So in this case, x comma y1, x comma y2, this can only be possible if y1 and y2 is both are same, both are equal. So this is true for all x, y1, y2. If they are same, this can be possible. Otherwise, for all x, x belongs to A. For that, that implies there exists some y such that y belongs to B, set B, and x comma y belongs to f. And in this case, we have only one y, so no need to worry. But if we have more than one y's, then these y's values should be equal. Otherwise, it is not a function. All right. So here let's discuss some terminologies about the functions. So given a function f such that uh, A maps B, we say that mapping f maps A to B, or f is mapping from A to B. So these are different ways to call it. You can call f such that A implies B. You can say f is the mapping of A to B. You can say f is mapping from A to B, whatever you want to say. These all are the terminologies that are being used. But in all those scenario, if this is a function, given this is a function f, then this A, set A, is called the domain of this function. If this is a function f, right, that maps one element of A to the element of B, then this set A is called the domain of f. All right. And this set B is called codomain of f, right? So this A is the domain, right? And this B is the codomain, right? And then when A is mapped to B, this B is basically mapped to A with the function f. We call B is equal to fa, right? Or fa is equal to B. We already discussed in the previous slide. In this case, B, this B in set B is called an image of A, right? This B is called image of A, right? Clear? And then this A is called pre-image of B. This A is called pre-image of B, right? So this f is a function. This whole set A is called domain. This whole set B is called codomain. The mapping element A is called pre-image of the element B, and B that is mapped to A is called the image of A, right? So this is image of A in this set B. This is pre-image of B in this set A. All right. And then there is an other terminology that we call range. What do we mean by range? The range of function f is the set of all images of points in A under f, right? What does it mean? That means the range of this function f. Okay, so we have this complete set A, but that does not mean all the elements are mapped to some of the element, right? So for example, there are A, B, C, D, E elements, and here we have 1 2 3 4 5 elements, right? And then some of the elements may be mapped to B, some of the elements are remaining. So the complete set is called domain, and all those elements that are mapped, subset of those elements is called range, right? And we denote it with f of A. This is range. So the range of f, function f, is the set of all images, right? The images here in the set B of points in A, right? So set of all the images here that are mapped, right, uh, from the set A, right? We denote it by f of a. So for example, if we have, let me take the example here, this one from the first slide. So we have set A of the students and B of the grades, right? So A is mapped, Ruby is mapped to A, Sandeep is mapped to B, Williams is mapped to B, um, uh, and then Kathy is mapped to A, right? So this all set of students are the domain, this domain, right? All the students, all these set of grades are called codomain, right? This is codomain. And then what is range? Only those elements that are mapped. This one, right? This is called range, right? This is the range. So all the set of images, right? These are the images, these are the pre-images. So set of images is called a range of the function f, and we denote this range by with the function f of A, right? So this is the range, that is A and B. Is that clear? So now let's come back to this example. So the range of f is the set of all images of points in A under F, set of all images in point A under this F, we denote it with f of A. So when two functions are equal, so two functions are equal when they have the same domain, obviously same set A, the same codomain, same set B, and map each element of the domain to the same element of the codomain. Then we call these two functions are equal, right? Okay, so how we can represent the functions? There are three ways to represent a function. An explicit statement of the assignment, like the student and grade example. So we have this explicit statement like Sandeep has A grade. So grading students to grade mapping, right? Courses to teacher mapping, right? Multiple courses, multiple teachers. So which course will be assigned to what teacher? So there is one way, or the first way, explicit statement. Multiple courses are available, multiple students are available. What students are taking what courses? So the students are mapped to the courses. So many examples are there. In a shopping mall, there are number of products, there are number of customers. So what customers are choosing what products or buying what products, you can always map. There may be one function that can map the behavior of the customers, right? So the explicit statements is one of the way to represent the function. Then this is a mathematical way, a formula. We already know that f of x is equal to x plus 1, or f of x is equal to x square, or f of x is equal to 2x square plus x plus 3. Also, any formula can be mathematical formula. These all are the mathematical functions. We know that we are using those functions since our primary schools, right? Then another representation is the computer programs. So we always write the computer programs in the programming languages. Like for example, if you are familiar with the Java, right, or the C++, so you always write int void int main, and then you write some arguments. This main is a function that takes some arguments and return the integer value, right? So for example, you are writing a user defined function, int add, and then you are taking x comma y. So what does it mean? This is a function add that takes two arguments, two values, and it it sums those values and return an integer value as a returning value, right? So one more example written here is a Java program that, when given an integer n, produces the nth Fibonacci number. So what are the Fibonacci numbers? You might be familiar with this. If not, just wait, we will be discussing the Fibonacci numbers in detail in the upcoming chapters. But so far the Fibonacci numbers are very interesting. I mean, they have wide applications in nature, wide applications in computer science. So the Fibonacci numbers are like one, right? One, right? Um, okay, 1, 2, 3, 5, 8, 13, right? Okay, and then 13, um, then 21. So and so on, so on, so on. So these are the Fibonacci numbers. What is the series? How these are performed? So the next number is the sum of previous two. So for example, this number, the third Fibonacci number, is the sum of first Fibonacci number and the second Fibonacci number, right? So that is 1 plus 2 is 3. So this number, right? The fifth Fibonacci number is sum of the fourth and fifth Fibonacci number. So for 8, so third and fourth Fibonacci number, 3 plus 5 is 8. So similarly, for example, if I want to find the f of Fibonacci number of seventh Fibonacci number, that is nothing but Fibonacci number of 6 plus Fibonacci of um, 5, right? So this is how they are formed. So that's the seventh Fibonacci number. So this is again a program that returns such value, seventh Fibonacci number, by taking two arguments, right? So a Java program, when given an integer n, produces the nth Fibonacci number. So you give an integer 7, you may be interested to find the 21st Fibonacci number or 30th Fibonacci number. So 30th n is 30, and you want to produce is, that is f of 29 plus f of 28, 8, right? So what is that, and how is, I mean, this is just to give you the example how we actually represent the functions. So three methods: explicit statements, a mathematical formula, or a computer program. Okay, so a few questions or the few revisions. Say for example, if this is the set A and this is the set B. Set A is A, B, C, D, 4 elements, and set B has 3 elements, X, Y, and Z. So what is f of A? What do we mean by f of A? F of A means if we map A from set A with the function f to set B. So what is f of A? In other words, what is the image of A? So, so you can see A is mapping to Z. So definitely it would be Z, right? The image of D is, what is the image of D? Obviously D is mapping Z, so Z is the image and D is the pre-image. So image of D is again Z, all right? So the domain of F. So what is the domain of F? So we already know that the domain is the set A. I mean the set from which the elements are being mapped. So the domain is nothing but set A, that is A, B, C, and D. So the whole set A is the domain of this F, function F. What is the codomain? As I mentioned earlier, the codomain is the set B from where we are mapping, I mean, on which we are mapping the elements, I mean, from A to B. So B is the codomain. So that is the X, Y, and Z. All elements are in the codomain. So the complete set B is the codomain. What is the pre-image of Y? The pre-image of Y, you can see Y is being mapped with the function f of B, right? Isn't it? So Y is equal to this one. So the pre-image is B, right? So you can see the pre-image is B. What is the f of a? F of a, as I mentioned earlier, this is nothing but the range. We f of a with the capital A is the range, right? What is the range of this set A? So this x, y, and z are the codomain, and all the elements that have some image, some pre-image, right? Those are mapped, are called the domain. So in this case, only y and z are the are mapped. So these two elements are the range of this set A, a function f of A. All right. So the pre-image of or pre-images of Z is, so Z is mapped by multiple members from A. So the pre-images of Z is A, C, and D. All right. Okay. So, um, so for example, another question: if f is a function from A to B, right? F maps A from A to B, and S is a subset of A, right? So S is a subset of this set A. I mean this set A. So then f of S is, right? F of S means range of S. F of S such that S belongs to the capital S. S belongs to that subset of A. All right. So f of A, B, C is, what is f of A, B, C is? So f of A, B, and C is, you can see f of A is mapped to Z, B is mapped to Y, and C is mapped to Z, right? So f of this three is Y and Z. Okay. So what is f of C and D? So you can see this is not the complete set A. This is not the complete set. This is the subset of this A, right? So that's why the range is again the subset that from those members that they have mapped in B, we will consider only those members as a domain. So what is f of C comma D? So you can see C and D both are mapping to Z. So the range of this subset CD is Z, right? Okay, now let's talk about the different types of the function. So the first type of the function, we call it the injections, or we call it one-to-one function, right? So let's see the formal definition, and then I will explain it. So a function f is said to be one-to-one, right? Or we call it injective function, right? When, if and only if, the condition is if and only if f of A equal to f of B implies that A equal to B, right? For all A and B in the domain of F. What does it mean? This means, as the name suggests, one to one. So all the elements in B, or in a short, in a straightforward manner, all the images have only one pre-image. Listen again carefully. All the images have only one pre-image. Other way, all the elements are mapped by exactly one element. All the elements in B are mapped by exactly one element. In previous example, here you can see this Z is mapped by A, C, and D. If we are talking about the injective functions or one-to-one function, this is not allowed. So no element will be mapped by multiple elements in A. So A is mapped to Z, that is exactly one element. W is the image, it has only one pre-image. Z is the image, it has only one pre-image. Y is the image, it has only one pre-image. X is an image and it has only one pre-image, that is C. Is that clear? So what does it mean? It says, now listen carefully again, if and only if f of A is equal to f of B implies that A equal to B. Listen here. So if we have, see in this animation, if we have two elements, see now, A1 and A2. So they are mapped to two different elements. But if they are mapping to the same element, it means these are the same element as well. A1 and A2 are the same element, right? So if A1 equal to f of A1 equal to f of A2 in B, then A1 equal to A2. So if we have two different mappings, so it means we have two different elements in A as well. But if they are the same element, so it means the elements in set A are also the same, right? Or in shorter way, one element will map to the one element only. That's why we call it one to one, straightforwardly, right? So once again, let me read the definition. A function f is said to be one to one or injective if and only if f of a equal to f of b implies that a equal to b for all a and b in the domain of y, for all a and b in the domain of f, right? A function is said to be an injection if it is one to one, right? I hope this is now clear, right? So all so you can see v is element in b in the codomain, but that is not mapped by any element. It's okay, this is allowed, right? This may be happen that some element may not have an pre-image in set A. It's allowed. That is, then this V is not part of the range. But this is not allowed that Y is mapped with multiple. So for example, if this is the scenario, so Y have two pre-images. One is B, another one is C. So this is not allowed. If this is a scenario, then this is not the one-to-one function. If all the images have the single pre-image, all the image elements are mapped with only one element, then we call it the one-to-one function or the injective function. All right. The second type of the function is called surjective. Surjection. So surjective function is a function from A to B is called onto function. Surjective functions are also called onto function. Injective function are called one to one, whereas surjective functions are called onto functions. So if and only if it is onto or surjective, if and only if for every element B belongs to B, there is an element A belongs to A with f of A is equal to B, right? What does it mean? Let's understand this. It means all the elements in codomain, right? All the elements in B, they have a pre-image in set A, right? One to one, in one to one we were having the restriction that all the pre-images all the images have exactly one pre-image. Here you can see Z have multiple pre-images. Z is mapped by A as well as D. No matter, it is allowed in surjective function, but it cannot happen that we have a one element V and it does not have a pre-image in set A. No, this is not allowed in onto function. So what does it mean? In onto function, all the elements in set B must have a pre image in set A, right? So no element in set B has is left without mapping. So that's what it says. A function f A to B is called onto or surjective if and only if for every element B that belongs to set B, there is an element A that belongs to set A with function with this mapping, right? So that is mapped from A to B. So a function f is called a surjection if it is onto, right? So here you can see in this animation, so the surjective functions are called the onto function. Clearly you can see the range of A, the range of A is complete codomain B. So range of A is B, the whole set B, right? The whole codomain. So that means all the elements are mapped with at least one of the with exactly one of the element in A. So here you can see if there is a function A element A that should be mapped to every function, every element of set B. All right. For every B belongs to B, B must have a pre-image in such that it belongs to set A. Right. So these two things should be clear. One is the one-to-one. In one-to-one, the condition was uh, every pre-image, every image must have only one pre-image in set A, right? But in onto function or the surjective function, the condition is every element in set B must have a pre-image in set A, right? The third type of the function is the bijective function or the bijection, right? This is also called one to one again. I mean, bijection is also the condition is one to one, right? So a function is a one to one correspondence or a bijection if it is both one to one and onto. So a function that has both properties, if it is a one to one and injection, and it is injective function as well as the surjective function, then we call it a bijective function or the bijunction. So for example, in this example, you can see the injective. Injective means every one to one. Injective mean one to one, right? So you can see all the X has only one pre-image, Y has only one pre-image, Z has only one pre-image, W has only one pre-image. So that means it is one to one function or the injective function. And the second condition, surjective, you can see no element is left in set B that do not have a pre-image in set A. So it is also as well the onto function. So such type of function is called uh, bijective function, right? So you can see in the animation here, so F is both surjective and injective. This is a necessary condition. And all the elements you can see are mapped onto A, and both conditions are fulfilled if there is an element one to one and as well as onto function, right? So now from here, we conclude that the one thing, or we should lead this to one thing, that the inverse function that we will discuss later in few slides. So only those functions have the inverse. Those are the bijective functions, right? So the bijective functions have the inverse, or one-to-one function have the inverse functions, right? What is the reason? Why is it? And what are the inverse functions? We'll be discussing shortly. So just to conclude, you can see from here, this is not a function. Why? Because A is mapping to multiple, as I mentioned earlier. So for example, this is the student Sandeep. It cannot have the A grade and B grade at the same time. So this A element, any element from A cannot map to multiple elements of the B. So this is not a function. We do not call it a function, right? So this is the general definition of the function. We have some elements in set A, we have some elements in set B, and then the function f is basically the mapping of the element from A to B, and we can see that. This is the definition of the injective function, example of the injective function. What does it mean? It is one to one. So all the elements are mapped one to one. All the images have one pre-image, not more than. So B cannot have many A's, right? So surjective function is every B has some A. I mean, every image has some pre-image. So no matter, for example, this have multiple pre-images, no problem, but at least it has a pre-image. And this is the definition of the bijective function, where you can see this is one to one, as well as this is the onto, no element is left. So in this diagram, you can clearly understand the difference between the what is a function, what is a journal function, what is the injective function, surjective function, and bijective function. All right. So now how we can prove that the function f is one to one or it is an onto function. So here are some strategies. Suppose there is a function f that maps A to B. So to show that f is injective, show that how you can do that. If it is an injective, show that if f of x is equal to f of y for any arbitrary x and y that belongs to A, with x is not equal to y. If this is true, then that means f is then that means this function f is the injective function. What does that mean? That this means if x and y are not equal, and you can prove that, then there should be this is the x equal to y. For some values we can I mean do some mapping, and then we will see some examples in the coming slides as well, to show that f is not injective, right? If it is not injective, then find a particular element x comma y that belongs to A, such that x and y are not equal, and they are not same, x and y are not same, and but the mapping, the image pre-images are not same, but the images are same. To find some element, and then you will prove it that it is not an injective function, right? So if you want to show that f is the surjective function, so consider an arbitrary element y that belongs to B and find an element x that belongs to A, such that, right? Such that f of x is equal to y. What does that mean? That means y is image of x, right? And f of x, if they have the same thing, then you can see this is the surjective function. That means for every y, that arbitrary point, there is a pre-image in x that is mapped with f. To show that f is not surjective, find a particular y that belongs to P such that f of x does not have any y, is not equal to y for all x belongs to A. If it is, there is a any single element, if you can find it from the set B that is not mapped, you can easily prove that this is not surjective. All right. Here is some examples showing that f is one to one or onto. So for example, in the example one, you can see let f be the function f uh, from a set having elements a, b, c, d to the set having elements 1, 2, 3, defined by f of a is equal to 3, f of b is equal to. What does it mean? If I can just draw it, then it may be easy to understand. So for example, what does it says is it's a function having elements a, b, c, and d, right? And then there are elements 1, 2, and 3, right? And then it says there is a function f that maps the elements. How it is mapping? It says f of a is mapped on 3. That means a is mapped on 3. This a is mapped to 3, right? F of B is mapped to 2. B is mapped to 2, right? And then what does it says? F of C is equal to 3. C is mapped to 1, right? And D is mapped to 3. D is mapped to 3. Now, if we have mapped this function, now what we need to prove is f an onto function? Means surjective function. Yes, it is onto or surjective function, since there is no element left in the set B here in the codomain. All 1, 2, 3 have the images in set A. So since f is onto, since all three elements of the codomain are images of elements in the domain, right? We represented it in the diagram here. If the okay, now what if we have the we add the codomain one more element 4 here? So for example, I add 4 here. Is it the onto function now? No, it is not the onto function now. If I add the 0 here, so it is not the onto function. Why? Because these are the elements that are not mapped. They do not have the pre-image in set A. So then it is not the onto function. But if these are not, there are only 1, 2, 3 elements, then this is the perfectly onto function. So another example is the function f of x is equal to x square from the set of integers to the set of integers onto. So we have the set of integers z, right, to that maps to z, right? So this is a function f that maps z to z, and the question is the function from the set okay onto, is it onto? So you can see every the function is f of x is equal to x square. What does that mean? Let me just test this for some values. So this is set A, for example, this is set B. and f of x is equal to x square. So for example, if I take x as 1, right, since these are the integers, I can take any of the integer, right? So the x of x square is 1, so 1 is mapped to 1. So this is also integer, this is also integer. Say for example, if I take I take 2, so this square is 4. Obviously 4 is a member of this set b, that is integer, so this is also mapped. But then you can see 3 is not mapped to any of the element, so 3 is left, right? That means 3 is not the perfect square of any element, any number. So how can it be the onto function, right? So that's why this is not the onto function. No, f is not onto, because there is no integer x, just for example -1, right? So since this is a set of integer, that may have the negative integer as well. So if this is -1 here, right, or -1 here as well, so -1 is not the perfect square of anything, but -1 has the maybe the square of the that is positive one. But what about this one, this -1? This will never get mapped. Or 3, this will never get mapped. So that's why this is not onto function, right? So you understand how we are going to prove the functions, that whether it is on to or one to one, right? Okay, what do we mean by the inverse function? Remember, so we can only find the inverse function of a bijective function or a bijunction function, right? So let's see the definition. Let f be a bijection function from a to b, right? Then the inverse of f, denoted by f inverse, that is -1, f to the power of -1, is a function from b to a defined by f inverse of y is equal to x, if and only if f of x is equal to y, right? So since y is equal to f of x, f inverse of y is x, right? Say, so just let's have one example here. In this diagram you can see this is a element a that is mapped to element b, right? So a is mapped to element b with the function f of a, right? uh, and a is the image, sorry, b is the image, a is the pre-image, and that is mapped with f of a, right? Since it is a bijective function, bijective means one-to-one function. I mean, we have the one-to-one. I mean, the pre-image has all. The image has only one pre-image. We can have the inverse of that. That is f inverse of b. That means this can be mapped with the inverse function in a reverse direction, in a different with the inverse arrow, and this is mapped with f inverse of b. Then what happens, this a becomes this a becomes the image, and this b becomes the pre-image of this f inverse of b, right? So inverse function inverses the everything, reverts the everything. So we map the elements of A with the help of F, right? A to B, and F inverse do the reverse thing, that maps the element of B to the element of A, right? So here in this diagram, you can see this is the function F that has mapped here, and then F inverse is mapping from B to A. All right. So F inverse sends B that belongs to B to a set F inverse of B that is a subset of A, right? So F inverse send all B to A. All right. But the question is, no inverse exists until F is a bijection. Why? So if the function is not one to one, can we find the inverse? So for example, if I have an element A, B, C, and then here I have 1, 2, 3, and then this is mapped with some function f, right? A is mapped to 1, right? B is mapped to 2, and C is also mapped to 2, right? So this is basically f of A, this is basically f of B, as well as f of C, right? So we cannot do this since this 2 has multiple pre-images. So if we reverse it, what will happen if I reverse it? So this is function f, right? So if by definition of f inverse, what will happen? A, B, C, 1, 2, 3, isn't it? So what will happen? This one, with the help of this F inverse, 1 will map A, 2 will map B, 2 will also map C. Then this violates the definition of the function. This is no more a function. That's the reason the function should be one-to-one, and in bijunction function, when we are going to find the inverse. So you cannot find the inverse of all the functions. You can only find the inverse of the bijective functions. All right. So So now let's see some examples of this inverse as we were just looking around. So here you can see this is a function A having some elements A, B, C, D, and a function B some elements V, W, X, and Y. And you can see this is 1 2, this is a bijective function, this is 1 to 1, and this is on to as well. Since this is the bijective function, we can find the inverse of that. So the inverse is, if A is mapping to Y, in the inverse function Y is mapping to A. So you can see Y is mapping to A. So we just reverse the arrows and we reverse all the things. V is mapping to D now. Here D is mapping to V. So in the inverse function, or in the function, we actually maps the element from set A to B, right? And in the inverse function, we map the set from B to A. In function, we have images in B and pre-images in set A. In inverse function, we have images in set A and pre-images in set B. So everything is reversed actually. Okay. So here is one example. So let f be the function from a, b, c to 1, 2, 3, right? So 3 elements in set A, 3 elements in set B, such that f of a, and now the mapping is a is mapped to 2, b is mapped to 3, and c is mapped to 1. Is f invertible, and if so, what is its invert? So now tell me, is it inversible or not? Since a is mapped to 2, b is mapped to 3, c is mapped to 1. So first of all, we need to check whether it is a bijective function or not, one-to-one function or not. So a is to b, b is to c, b is to a maps to 2, B maps to 3, and C maps to 1. Yes, it is a bijective function, and we can find the inverse. So if we can find the inverse, what would be that? So that means f of 2 maps A, f of 3 maps B, f of 1 maps C. So let's see the definition. Solution. So the function f is invertible because it is one-to-one correspondence. So the inverse function f inverse reverses the correspondence given by f. So f inverse of 1 is equal to c, f inverse of 2 is equal to a, and f inverse of 3 is equal to b, as I discussed earlier. So you can pause here and you can understand if how we have done the reverse if you do not understand still yet. One more example. Okay, so let f is a function that maps z to z, integer to integer, be such that f of x is equal to x plus 1. Is f invertible? And if so, what is it inverses? So now this is interesting. So how we can see that? So since they are the same set, so say for example, if x is equal to 1, right? So in from it 1 is mapped to 2, 2 is mapped to 3, 3 is mapped to 4, 4 is mapped to 5, 5 is mapped to 6, 100 is mapped to 101, 101, 3 is mapped to 104. So with the help of this function, we have the one-to-one correspondence, isn't it? So there is no I mean there is this is the bijective function. So for example, it cannot happen if I have x is equal to 95. So it will always be mapped to 96, right? It cannot map to the I mean multiple. It may not have the multiple images in set B. So since it is the one-to-one function, we can have the inverse of that. And then what is the inverse? Let's see. So definitely the function f is invertible because it is one-to-one correspondence. The inverse f inverse is f inverse of y is equal to definitely y minus 1. So if f of x is equal to x plus 1, so inverse is y minus 1, right? And then you can always take some values and you can prove that. One more example. Let f is a function from R to R, mapping of real number to real number, be such that f of x is equal to x square. Now, if x is f invertible, and if so, what is it inverse? So we already seen that this is not the one-to-one correspondence. Why? So for example, if we take the x value as 1, or for example, if I take the x value as, okay, let's say if I take the x value as 1, so the x square is 1. If I take the x value as -1, it is also 1. So that means 1 and -1, they both are mapping to 1, isn't it? So from the real set of real number, 1 is also mapping to 1, -1 is also mapping to 1. So that means this is not one-to-one correspondence. This is not a bijective function. Since it is not bijective function, we cannot compute the inverse of this function, right? Just one more example. So for example, the if I take x as equal to 4, so this will be mapped to 16 since it is 4 square. And if I take -4, this will also be mapped to 16, right? So two different elements from the real number are mapping to the same element. So that's why this is not the uh, bijective or the one-to-one correspondence. That's why it's not possible to compute the inverse of this function, right? Okay. Now let's talk about the composition of function. What do we mean by the composition? Composition means we are composing two or more functions. Say for example, let's understand it from this diagram first. If I have a set A and I have a set B and I have a set C, from set A to set B, I can map the elements of A to element of B with the help of function G, right? I have a function, just 1 minute, sorry for this, let me erase this. Okay, so for this A to B, I have a function G that maps the element of set A to set B. And then this element, all the elements of B are mapped to another set, that is C, with the help of one function F, right? So what does that mean? All the elements of A are mapped to B and B's elements are mapped to C. So if this is a scenario, I can directly map the elements of A to C. How? See, if this is mapped with G, A is mapping A to B is with the help of G, and from B to C with the help of F. I can compute directly, and we call it F of G, FOG. We use this small circle F of G, right? You might be worried that why we have written it in reverse form, this F and then G. So I will explain it just in few seconds. So let's see the definition first, or before that let's see this animation first. So a set A, B and C. Set A is mapped to set B with a function F, right? Here it was G, here it is F, and set B is mapping all the elements to set C with a function that is G, right? Clear? So we can directly map, we can compose these two functions F and G and directly map from A to C with G of F. Here you can again see we have reversed the order. So let's see the definition. Let F is a function, B maps C here, B maps C, F is a function that maps B to C, and G is a function that maps A to B. The composition of F with G, denoted by F of G, right, is the function from A to C determined by like this. F of G of X is basically equal to F of G of X. What does that mean? If I am going to map, okay, so let's take one example. So for example, this is A, B, C. This is 1, 2, 3. This is X, Y, and Z. A is mapped to 1, B is mapped to 3, C is mapped to 2 by function G. And with the help of F, this 1 is mapped to Y, this 2 is mapped to X, and 3 is mapped to Z with the function F. All right. And then if we can compose these two functions G and F, we can directly map it to the A to C, right? Since A is mapping to 1 and 1 is mapping to Y. So I can say that this this A, I mean, this A, A can map to Y directly by composing G and F. How we can compose that? First of all, I will find the mapping of this F, right? Mapping of this F first, all right? Okay, mapping of this G first. So on A, from A to B, A is being mapped to 1. That G will determine. So first of all, I need to compute this G of X in order to map directly from A to C. So first of all, I need to compute this first, right? And then once I found the value of G, G of X, that is A to 1, that is 1, right? That is 1. Then I can directly see what is the F of 1. F of 1 is Y, right? So in this way, I can see the result of this is Y. So what does it mean? I can directly map this X, that was A, right, directly to Y. I hope you understand this point, right? Let me take one more example. So for example, this C, I can map, I first of all I map this C to 2 with the help of G, right? That is 2, right? And then with the help of F, I map this 2 to Y, 2 to X, right? So indirectly, first of all, I need to know how I map this C to 2, that with the help of G. So this is resulting in 2. So G of X will result in 2, right? And then I will find the F of 2, that is X, right? So I will get X. I mean, this, or in short, I will see C is mapped to X, right? Clear? So now let's see the definition again, once again. B maps to C, F is a function such that B maps to C, and G is a function such that A maps to B. The composition of F with G, denoted by F of G, is the function from A to C defined by F of G of A, G of X is equal to F of G of X. So you know that why we are doing this, why we are doing in a reverse form. Why did we write F first and then we write G first? Because first of all we need to compute this G, and then we can only find with F, right? So let's discuss further, and we will see the examples in incoming slides. Here in this slide, we can see the example that I mentioned in the previous slide. Here you can see we have a function A to B, that is G. So A to B mapping is with the function G, and B to C mapping is with function F, right? And then we can directly map it with A to C with the help of this composition F of G, if we know that, right? So first of all, we need to compute this G. So for example, just A is mapped to Y, that will return with G. So we already computed this G, that is returning Y, right? And then we can compute F of Y. So F of Y is this one, that is Y to J. So directly F of G we can write A to J, A to J, right? So one more example. B is mapped to W with G. So we computed G, right, first, right? And then we see that W is mapped to H with F. So that means if we compute that, that is B mapped to H directly, right? And similarly, all the elements are mapped. Okay. So let's take some real examples. So for example, if f of x is equal to x square and g of x is equal to 2x plus 1. So let's compute the f of g of x. So we know that what is the g of x? What is the g of x? G of x is 2x plus 1, right? And what is, we have to put the value of g of x in f of x. So the value of g of x is 2x plus 1 and f of x is x square. So instead of this x, we will put we will substitute the value of this whole, right? G of x. So that is nothing but 2x plus 1 and this square is square. So that's the result of f of g of x. Or in short, we can write f of g of x, right? Okay, g of f of x. So we know that what is f of x? F of x is x square, and we need to substitute x square in gx, right? So gx is 2x plus 1. So instead of x, we are going to substitute the value of fx, that is x square. So 2x square plus 1 will be the g of x, or in short, we call g of f of x. So that means one conclusion point here is f of g is not equal to g of f. They both have the different meanings. All right, clear. Next, let's take one example. Let g be the function from the set a, b, c to itself such that, now see, it is function a to b, a, b, c to itself such that g of a is equal to b, I mean is mapped with function g to itself, and the result is g of a is b, g of b is c, and g of c is a. Let f, that is another function, be the function from the set abc to the set 1, 2, 3 such that f of a is equal to 3, f of b is equal to 2, and f of c is equal to 1. What is the composition of f and g, and what is the composition of g and f? So composition of f and g means we are interested to find f of g for all the elements. For all the elements means for f of g of a, for example, and f of g of b and f of g of c as well, right? So now let's see how we are going to compute it. So f of g of a is basically nothing but f of g of a, right? That is g of a, and we know that g of a is what? B. So we'll substitute the value of g of a in this. So that is f of b. F of b is mapped to 2. So f of g of a is nothing but 2. Clear? Now let's see f of g of b. So that is nothing but f of g of b. So g of b is c. So we need to substitute the value of g of b, that is c. So we got f of c. So f of c is 1. All right. Now f of g is of c. That means f of g of c. So g of c is what? G of c is a. So that means we need to compute f of a. F of a is mapped with 3. That's how we have computed f of g. Since g of f is not defined, why? Because the range of f is not a subset of the domain of g, right? So it's not the subset of the domain of f is not the subset of the domain of g. That's why it is mapping to itself, right? A, B, C is mapping to itself with the function g. So we cannot compute g to f, right? Okay. One more example. Let f and g be functions from the sets of integer to the set of integer defined by fx, I mean z to z, right? F maps z to z. Okay. So such that f of x is equal to 2x plus 3 and g of x is equal to 3x plus 2. What is the composition of f and g? And also the composition of g and f. So how we can compute that? Let's see. So f of g of x means f of g of x. So we know that what is the value of the g of x? G of x is 3x plus 2. So we need to substitute 3x plus 2 in fx. So that is 3x plus 2. So what is fx? That is 2x plus 3. So instead of this x, we will substitute the value of gx. So they substitute the value of this one. So instead of this x. So 2 into 3x plus 2 plus 3. right? So if you simplify this, this is nothing but 6x plus 4 plus 3, that is nothing but 6x plus 7. And now you got the idea what we are going to do in the g of x. G of x is what is the value of the fx. We know the value of the fx is 2x plus 3. So substitute it here, 2x plus 3. And now substitute this 2x plus 3 in the value of gx. Gx is 3x plus 2. Instead of this x, substitute the value of fx, that is 2x plus 3. So 3 into 2x plus 3 plus 2. And if you simplify this, this is nothing but 6x plus 9 plus 2, that is not simplified with 6x plus 11. Right? So this is how we are going to compose different function or to for the mapping purposes. Right? Now let's see how we can draw the, how we can graph the functions, how we can represent the function with the help of the graphs. Let f be a function from the set A to set B. The graph of the function f is the set of ordered pairs AB such that A belongs to A and f of A belongs to B. And that's true basically. Let's see how. So for example, let's say for example we have a function fn, right? Fn is a function that is equal to 2n plus 1, or fx is equal to 2x plus 1. I mean, you can take n or x, whatever. So this is x-axis. Fx, this value is the uh, this value, the returning value is the y. We already know that y is equal to fx, isn't it? We already computed it. So this is the fy value, and this, the value that we are going to substitute here instead of n is the x-axis. So this value is at the x-axis, the returning value is at the y-axis. Okay, so now say for example I have this value. If I substitute it 0, n is equal to 0, then what happens? So the returning value is 1 only, right? So that means the ordered pair will be returned, that is 0 comma 1, isn't it? So 0 is on x-axis, 1 is on the y-axis. So here you can see at the 0 at the x, when x is 0, y is getting 1, right? So let's substitute another value. If I take n equal to 1, then what will happen? I will get another ordered pair. That is what? At 1, I am going to get 2 plus 1, that is 3, right? So this value is basically 0 comma 1. Come on. Just 1 minute. I don't know why this pen behaves nasty sometimes. Okay. So this is 0 comma 1, right? So when I put 1 as n, the result is 3. So at 1, when x-axis is 1, the value is 1, 2, 3. At y-axis it is 3, that is 1 comma 3, right? And if I substitute 2, then what happens? At when n is 2, when means at x-axis when x is 2, this becomes 4 plus 1, that is 5. So 5. So I got an ordered pair, that is 3 comma 5, right? Now let's substitute some negative values as well. So for example, if I substitute negative 1, so if I substitute negative 1, what happens? When x is negative 1, that is this one, right? So this becomes negative 2 plus 1, that is negative 1. So that means here, and when this is negative 1, this y-axis is also negative 1. So I will get this point. I will get this point, right? So that is negative 1 comma negative 1, right? This one. Okay. Then if I substitute it negative 2, so what happens? At the negative 2 means this axis, at this x value, I am going to get negative 4 plus 1, that is 3. So I will get some value that is here, something here at y, right? Do you understand my point? So you can see how we can plot a graph. So if you see, this function is the linear function, since you can see that we are getting the linear function, right? So this function is the linear function. So we can always plot the function on a graph, right? So let's say one more example, f of x is equal to x square. This will also return the ordered pair. So for example, if I take x is equal to 0, so obviously the square root is also x square is 0, square is also 0. So this is 0 comma 0. So that is 0. If I take 1, x is equal to 1, this will become 1. So this is 1 comma 1. At when x is equal to 1, this is, so here you can see it in the graphical representation as well. So you can see in the animation, right? So if x is equal to 2, that will become 4. So when x approach is 2, y becomes 4, right? And then if you see x is equal to 3, y becomes 9. Same happens with the negative values. If you take negative 1, you will get 1, right? If you take negative 2, you will get 4. If you take negative 3, you will get negative 9. So function values are there. So if you see, this is nothing but a parabola, and it is a exponential function, right? So the function grows exponentially like this. Function grows exponentially like this, right? Since it is on the both sides, that's why we call it the parabola, right? So but the function is the exponential function. So that's how we can plot it on the sorry, how we can plot it on the graphs, right? So here you can see in this animation, this is how the graph of the r square, I mean in form of the square, is drawn, right? So if if there is any function given to you, mathematical function, you can always draw, you can represent the graph of that function, right? Now let's talk about some of the important functions. Three important functions that I discussed in the earlier. I mean at the start, one is the floor function, another one is the ceiling function, and then after that we'll see, we'll discuss about the factorial. So floor function, just to explain, let's say you are standing somewhere. So for example, this is someone, maybe you, right? You are standing obviously on the floor, right? And then on top of you there is a roof, right? So that's the similar concept that we are going to use here. So this concept, the ground value, the smallest value here is, this is called the this is the floor, and this is called the seal, right? Seal, right? So the floor function, and why I express this, let's just have a look. So for example, the floor is 1, right? And seal value is 2, right? And you get some value in between, and you have two functions. So for example, this floor function is represented with this function, this symbol, right? This shows these arrow shows this, we are using the floor function, I mean the lower side of this value, right? So what is the definition? Is the largest integer less than or equal to this x value. So for example, x is 0.3, right? X is 0.3. So oh sorry, 1.3. X is 1.3. So 1.3 is somewhere between 1 and 2, right? So what is the floor of 1.3? The floor of 1.3 is 1. That's what the largest value less than this, less than or equal to this x value. That is the round value, right? And what is the seal value? Seal value is this greatest value, right? So that is top value, that is 2. So the seal function is denoted by this sign is upward, and in the floor function this sign is the downward, right? Here are some examples. 3.5 seal. So 3.5 is the, so you can see, so the seal is the smallest integer greater than or equal to x. So x is 3.5, the smallest integer greater than or equal to x, that is the round number, right? We always get the real, I mean the decimal number, and then we need to get a round number or the integer number, right? So the greater value than 3.5 is 4, right? If we take the floor of 3.5, that is smallest value, smaller value than this one is 3.5 is 3, right? Similarly, if we talk about the negative 1.5, right? So this is the seal function. So seal function negative 1.5. So the largest value. So that is larger than this to the round is the negative 1, right? So as for example, you are standing here and then this is 0 and then this is -1, right? And then this is -2, right? And this is -1.5 in between. So obviously the greater value is -1, not the -2. So if you take the seal value, this will be -1. But if you take the floor value, this will be -2, right? So this is how we use the seal and the floor function. They are I mean, broadly used in programming languages, and you might be learning this in Java and in your C++ course, right? So let's have a look at the graph of the floor and the seal function. So for example, if you have, this is the floor function in this diagram A. So if you have a value between 0 and 1, right? So you can see the interval here. This 0 is included. This one is not included. This is excluded. This is open-ended. So if you have a value between 0 and 1, that is rounded to 1. Sorry, that is rounded to 0, right? 0 and 0.9. So that will be rounded to 0. That's because of the floor, right? So if you have a value between 1 and 1.9, that will be rounded to 1. So that's why this 1 is included, this 2 is not included, because if it is 1.9, still if you take the floor, that will be 1, right? Similarly, if you have the value of between 2 and 2.9, right? So that the floor 2.1, 2.2, 2.3, 2.4, if you take the floor of these values, that is always 2. That's why this end is closed and 3 is opened, right? Similarly, if you take the negative values, now here you can see if the value is between -1, right, -1 and -1, what does it mean? I mean, between the 0 and the -1, right? X-axis is 0, between 0 and -1. So starting from the -1 until 0.01, so the floor function will round it to the -1, right? So that's why this end is closed and this end is open. So you can see how we have a form graph. I mean, from this graph, you can see the functionality of the floor function. If we talk about the seal function, as I told you, if the value is between 1, 0.1, right, 0.1 to 1. So if the seal function is, if it is 0, this will definitely be 0. If it is greater than 0, that is 0.1 until 1. So seal function will make it, will round it to the 1. That's why 0 is not included here. 1 is included, is the closed circle, but where here it was in the open ended. I mean, it's a different. So if the value is from 1.1, 1 is not included, after 1 until 2, so that will be rounded to 2 in the seal function. So this is how the floor and seal functions are used, and they are very much common in implementing variety of computer programs, right? Some of the properties, important properties of the floor and seal function. Let's understand this. So for example, the first property is, if you are taking the floor of x, that is equal to n, it is possible if and only if x is greater than or equal to n and x is less than n plus 1. Let's take some examples. So for example, x is 1.5. X is equal to 1.5. So floor of 1.5 is nothing but 1, right? Isn't it? So what does it mean? X is greater than or equal to n. So you can see x is 1.5. That is definitely greater than 1, right? And it is less than n plus 1. That is 2. So the property says x, if you take a floor of some value x, it is equal to n, such that x is always greater than or equal to n, or it is less than n plus 1. Similarly, if you take this seal of x, right, that is equal to n. So let me take the same example again. X value is 1.5. So that says it is x is greater than n minus 1, and it is always less than or equal to n. So if you take the seal of 1.5, so n value will become 2, right? The upper value. So one seal of 1.5, let me write it here. Seal of 1.5 is equal to 2, right? So that means 1.5, x is 1.5. it should be greater than n minus 1. N minus 1 means n is 2, minus 1 means 1. So definitely 1.5 is greater than 1, that is true, and it should be less than or equal to n. So n is 2, so 1.5 is definitely less than or is less than 2. So that's why this property is, if you take the seal of some value x equal to n, it is that x is greater than n minus 1, and it is less than or equal to n. Another property, if you take the floor of x and then it is equal to n, it says then n is greater than x minus 1 and is always less than or equal to x. So the variables are interchanged. So you can see, let's take the same example. If I'm taking the floor of x, that is 1.5, the floor of 1.5, that is 1. So that means this n value, that is 1, definitely it is greater than x minus 1. So x is 1.5, x minus 1 is 0.5. So definitely 1 is greater than 0.5, and should be, this 1 should be less than or equal to x. So 1 is 1, n value is 1, and x value is 1.5. Obviously 1 is less than 1.5. So this is how these values are, these properties are proved and formed, and then these are very useful in some of the proving methods. We use these properties, right? Similarly, if we take the seal of x equal to n, if and only if, then this n is greater than or equal to x and is always less than x plus 1. So take the same example. If we take x is 1.5, if we take the seal, then the seal of x 1.5 is 2. So that says n is equal to 2, that should be greater than or equal to x. So x was 1.5, obviously 2 is greater than 1.5, and it should be less than x plus 1, that is 1.5 plus 1 is 2.5. So definitely 2 is less than 2.5. So these are all the properties. The second property of this floor and seal function is, if there is a function x, if there is a value x, the x, okay, the floor of this x is always greater than or equal to this x. That's obviously true. If x is 1.5, right? So the floor of x, that is uh, that is the floor of x is 1, right? So just 1 minute. Yeah. So if x value is 1.5, the floor is 1. So definitely 1.5 is greater than 1. And then it says it should be greater than x minus 1. Obviously, the floor of x is 1 and x minus 1 is 0.5. So 1 is always greater than 0.5. This is one side of this property. Another side is, if you take a seal of this x, so seal of this x is 2. So it says this is always smaller, x is always smaller than its seal. Yes, obviously it is true. And then this seal is always smaller than x plus 1. Obviously this 2 is less than 1.5 plus 1, that is 2.5. So this is how this property works. Third property is, if you take the floor of a negative value, that is equivalent to the negative outside and the seal of the function. Okay, let's say for example, if x is negative 1.5, if it is negative 1.5, so what will be the floor of this negative 1.5? So the negative 1.5, the floor of negative 1.5 is negative 2, right? So so that means if we take the seal of 1.5, that is also 2, right? And take the negative outside. I mean, take the if the result of this one is, result of this is negative 2, and if it is 1.5 again, right? And if you take the negative, so the seal of 1.5 is 2. If you need to apply this, so these two are same. Negative floor of negative x is equal to negative seal of x, right? Similarly here, a seal of negative x is equal to negative floor of x. So you can again prove it. So for example, if x is 1.5, if x is 1.5, so negative x is negative 1.5, so the seal is 1, right? And x is 1.5, so the floor is 1, right? Again, this is equal to the negative 1. I mean, both are similar, both are equal. The next property is floor of x plus n, right? N is some number that is the integer, and x is the decimal number. So, for example, x is 1.5 and n is 3, right? So that becomes 4.5. If you take the floor of 4.5, that is 4. That is similar to the floor of 1.5 plus n. So that is again 1 plus 3 is equal to 4. So no matters. I mean, you can take this number out. That whole number does not make any difference with floor and seal, right? So you can take all this whole number out whenever you are applying the whole floor and seal function. All right. The next is the factorial function. Factorial is okay. So it is a basically function that maps the natural number to the positive integers, that denoted by f of n is equal to n factorial. This symbol is sign of exclamation symbol is used for the factorial, is the product of the first n positive integers when n is a non-negative integer. So that means if you are going to compute the factorial of 3, that means n is equal to 3. So it is the product of first three integers, positive integers, right? So if n, that is f of n is 1 into 2 into 3 into 4 up till n, right? And when we compute the factorial of 0, this is always equal to 1. So let's have some examples. F of 1 is 1 factorial. So since this is the first number, so that is 1. Factorial of 2, that is 1 into 2. I mean, the product of first two numbers, that is 1 and 2. So that is 2. Factorial of 6, that is the product of first 6 number, 1 into 2 into 3 into 4 into 5 into 6, and you need to multiply 1 with 2, I mean multiply all this, and you will get 720. Factorial of 20, that means 1 into 2 into 3 into 4 into 5 multiplied by 6 7 8 until 20, first 20 numbers, and then you will compute the multiplication, and then you will get this result, right? So that's the factorial. Again, this is I mean widely used in computer science. In many of the algorithms you will learn in many courses in programming, as well as in data structure and algorithms. In upcoming courses you will learn this factorial function in detail. And then there is a formula in mathematics that is called Strilling's formula. This Strilling's formula is used to compute the n factorial. I mean, this is the short form. For example, if you are going to compute the factorial of 5, that is roughly equal to 2 pi n square root and n divided by e to the power of n. And I mean, you can substitute the value here, and you can, instead of computing all the multiplication, multiplying first 20 numbers or first 50 numbers or first 100 numbers, you can directly compute the factorial with this formula. And when another thing is, when f of n is equal to g of n, f of n is approximately equal to g of n when limit n approaches to infinity, f of n divided by g of n becomes 1. What does this mean is, don't worry about this. We are not going to discuss this in very detail. Uh, I am going to leave this for the rest of the courses, especially in the algorithm analysis course, where there we will discuss this Strilling's formula in detail. Okay. And the last topic now, partial function. Last topic for this video. What do we mean by a partial function? A partial function f from a set A to set B is an assignment to each element A in a subset of A called the domain of definition of f of a unique element B in the B. What does that mean? That mean if you have a function A, right? Set A, and you have a set B, and in the set A you have different elements, 1, 2, 3, so on, so on. For example, 100 elements. and in set B you have A, B, C, and so on up to Z, many elements. You are not going to map all the elements. You are taking one subset of this A, and you are going to map it on some of the subset of the B. Then we call the function that maps this subset to a subset of the B. This f function is called a partial function. And if it maps all the elements of A to the elements of B, then we call it a total function. So the partial function means all the elements of A are not mapped to B. A subset of A are mapped to B, right? Then we call it a partial function. If all the elements are mapped, then we call it a total function. So now let's come to the definition. A partial function f from a set A to set B is an assignment to each element A in a subset of A called the domain of definition of f of a unique element B in B, right? So with these are the conditions, the sets A and B are called the domain and codomain of f respectively. Obviously this is domain and this is the codomain. We say that f is undefined for elements in A that are not in the domain of definition of f. So rest of the elements you map this function f mapped a subset. Rest of the elements are undefined. That's what we are calling here. When the domain of definition of f equals A, we say that f is a total function. That means the domain is equal to A, not the subset, right? So that means all the elements are mapped. Then this is a total function. Then this is not a partial function. Here is one of the example. So f is a function that maps the natural number to the real numbers, such that f of n is equal to the square root of n. It is a partial function from Z to R where the domain of definition is the set of non-negative integers. Note that f is undefined for negative integers. So as discussed earlier, so for example, if we have the say for example, we know that we can easily compute the square root of positive numbers. We cannot compute the square root of the negative numbers, right? So since all the natural numbers, I mean from Z to R, since we are using the integers, that also includes the negative integers, right? So but the function is fn, we can only compute the square root of the positive integer. So this can map only the positive integer to the real numbers, right? It cannot map the non-negative it cannot map the negative numbers to the real numbers. So this is a partial number from the set of integers. This function can only map the the subset to the subset, that is the positive integers, to the to the real numbers, right? So that's why we call it the partial function. All right. So that's all about the functions. If you have any questions or the query, please do prepare your questions that we will discuss in the coming class. Until then, take care. And in the next class, we will discuss the new topic. Take care. Have a very good day. Bye-bye.